Hello and welcome back. In this video, I want to discuss the relationship between heat and temperature. And basically what heat is energy that is stored on a molecular, atomic, and subatomic scale, and is caused by the potential energy between these particles as well as their random motion. Now, because heat is a form of energy, the units of heat are given by joules. And when we talk about heat, we denote heat with this capital letter Q. So it turns out that for solids and liquids, the relationship between heat and temperature is fairly simple. So when you add some heat to an object, a change in the temperature is given by this formula here. So the heat that you add is going to be equal to some constant times the mass of the object times its change in temperature. So what this means is that the change in temperature is linearly proportional to the heat that's added. And hopefully it makes sense that this mass is here. So basically what this says is it says that the more massive an object is, the more heat that's required to change its temperature. So in other words, if you have, say, like a gallon of water, it will require more heat to heat up the gallon of water than it does to heat up a cup of water. Now, this constant C is called the specific heat, and it is a property of a material that describes how the temperature changes when it absorbs heat. Now, one of the types of problems that we'll study a lot in this class are the thermodynamic equilibrium problems. So two objects are said to be in thermodynamic equilibrium when there is no longer any exchange of heat between the two objects. Now, because temperature describes the tendency for an object to give or receive heat, thermodynamic equilibrium will only occur when the temperature of the two objects are equal. So let's go ahead and look at an example. So this example says an insulated cooler has 12 cans of Coke that are at 5 degrees Celsius. Each can has a mass of 0.35 kilograms and has a specific heat of 3,800 joules per kilogram degrees Celsius. Someone adds a 6.5 kilogram jug of water that is initially at a temperature of 27 degrees Celsius and has a specific heat of 4,186 joules per kilogram degrees Celsius. And the question asks us to determine the final temperature of the Coke and water after these objects achieve thermodynamic equilibrium. So let's start by writing the known and unknown variables. So what we were given the mass of the Coke is equal to 4.2 kilograms, and the mass of the water is equal to 6.5 kilograms. We were also told that the heat capacity, the specific heat of the Coke is equal to 3,800 joules per kilogram degrees Celsius, and that the specific heat of the water is equal to 4,186 joules per kilogram degrees Celsius. We're also told that the initial temperature of the Coke was equal to 5 degrees Celsius, and that the initial temperature of the water is equal to 27 degrees Celsius. And what we were asked to do is solve for the final temperature of the whole system. So one thing I should point out about this is that right away we can already say something. So we're putting in the Coke, well, the Coke is at 5 degrees Celsius, and we're adding this water, and the water is at 27 degrees Celsius. So we know that the final temperature of the system is going to be somewhere in between this 5 degrees Celsius and the 27 degrees Celsius. And because the water has a larger heat capacity and it has a larger mass, we expect that the temperature will be a little bit closer to the 27 degrees than it is to the 5 degrees. So let's go ahead and work this out. So the basic idea behind this is because heat is a form of energy, we can use conservation of energy. So the total change in the whole energy of the system is equal to the change in the heat of the Coke plus the change in the heat of the water. And if energy is conserved, then the total change of the energy is zero. So what this tells us is it tells us that the change in the heat of the Coke is equal to minus the change of the heat of the water. So basically what this relationship says, what this minus sign means, is this minus sign means that when the Coke gains heat from the water loses heat. So any heat that the Coke gains comes from the water. So now what we need to do is we need to plug in the relationship between heat and temperature. So remember that this is going to be equal to the specific heat for the Coke times the mass of the Coke times the change in the temperature of the Coke. And over here we have minus the specific heat for the water times the mass of the water times the change in the temperature of the water. And now the thing that we have to remember about this is that when objects reach thermodynamic equilibrium, the final temperatures of these two objects are going to be the same, but their initial temperatures are different, right? So the initial temperature of the Coke is 5 degrees Celsius, and the initial temperature of the water is 27 degrees Celsius. So these two delta T's, they're not the same, right? The final temperatures are going to be the same, but the initial temperatures aren't. So you have to be a little bit careful about that. So this is going to be the specific heat of the Coke times the mass of the Coke, and this is the final temperature of the whole system minus the initial temperature of the Coke. We have minus the specific heat of the water times the mass of the water times the final temperature of the system minus the initial temperature of the water. And now what we want to do is we want to take everything that has a T final and move it to one side. So let me go ahead, just to take it slow, I want to go ahead and multiply everything out. So let me go ahead and do this. So we'll have the specific heat of the Coke times the mass of the Coke times the final temperature minus the specific heat of the Coke times the mass of the Coke times the initial temperature of the Coke. Then we have minus the specific heat of the water times the mass of the water times the final temperature plus, because we have minus a negative, the specific heat of the water times the mass of the water times the initial temperature of the water. So what I want to do is I want to take everything that has a T final and move it to one side. So I'm going to take this term here, I'm going to move it to the other side. And I'm going to take everything else and move it to the opposite side. So I'm going to take this thing over here, I'm going to move it over there. So to move this over here, I'm going to add both sides by this, and to move this term over here to the right, I'm going to add both sides by this. So what I'm going to be left with is I'm going to have the specific heat for the Coke times the mass of the Coke times the final temperature plus, from this term over here, when I add this over, it's going to give the specific heat of the water times the mass of the water times its final temperature. And this is going to be equal to, so I'm going to move this over to the right side. This is the specific heat for the Coke times the mass of the Coke times the initial temperature of the Coke plus this term here, the specific heat for the water times the mass of the water times the initial temperature for the water. So now that we have two terms on the left that have T final, what I can do is I can factor out the T final. So this is the specific heat of the Coke times the mass of the Coke plus the specific heat of the water times the mass of the water times the final temperature. And over here we have the specific heat of the Coke, mass of the Coke, the initial temperature of the Coke, plus the specific heat of the water times the mass of the water times the initial temperature of the water. So to solve for the final temperature, I divide off this term right here. So if I divide this, then I'm going to see that the final temperature is equal to the specific heat of the Coke times the mass of the Coke times the initial temperature of the Coke plus the specific heat of the water times the mass of the water times the initial temperature of the water. And all of this is divided by the specific heat of the Coke times the mass of the Coke plus the specific heat of the water times the mass of the water. And so if you plug all this into a calculator, what we see is that it's going to be equal to 18.87 degrees Celsius. Now one thing I want to point out about this formula is a really nice way to think about this, is that basically this is a weighted average of the two initial temperatures. So the weighting that we get for the Coke is the specific heat of the Coke times the mass of the Coke. And the weighting we have for the temperature of the water is the specific heat of the water times the mass of the water. So like anytime you take an average where it's a weighted average, right, the way you do this is you have some weighting times one variable plus the weighting times the other variable, and then you divide it by the total weighting of the two things. So we're going to divide it by the specific heat of the Coke times the mass of the Coke plus the specific heat of the water times the mass of the water. But it's always going to come out like this. It's just going to be this weighted average of the two temperatures where the weighting is this mass times this specific heat. So the specific heat tells us what happens to the temperature when we add heat to a solid or a liquid. Now I want to consider what happens to the temperature of an object when it is undergoing a phase transition. So when substances undergo phase transition, the bonds between the molecules are altered, For example, when water boils, the hydrogen bonding between the water molecules is broken, and energy is required to break these bonds. So as a result, when you start adding heat to an object that is undergoing a phase transition, this heat is going to go into breaking and altering these bonds. The heat that's required to undergo a phase transition is called the latent heat. And the formula for the heat that's required to undergo a phase transition is fairly simple. So the heat that's required to undergo a phase transition is equal to the mass of the stuff that's undergoing the phase transition times this constant that's called the specific latent heat. And hopefully it makes sense that it's going to be proportional to the mass. This is the same idea that I talked about when we were discussing the specific heat. So basically the idea is that you're going to need more heat to boil off a gallon of water than is required to boil off, say, a cup of water. So the amount of heat that's required to undergo a phase transition is different for different types of phase transitions because there's different types of bonds that are being broken during the different phase transitions. So during a solid to liquid phase, we call the latent heat that describes this phase transition the latent heat of fusion, which is denoted with a subscript F. And when an object undergoes a liquid to gas transition, this is called the latent heat of vaporization, which is denoted with a subscript V. So what happens to the temperature of an object when the object undergoes a phase transition? Well, because all of the heat is going into altering the bonds of the atoms so that they can undergo this phase transition, any heat that's added goes into causing the phase transition and not changing the temperature. So for example, if I have something like a solid, when I add heat to the solid, it'll increase its temperature. And once the solid reaches its melting point, any heat that I add to the solid is going to go into breaking and altering the bonds to allow the solid to melt. So when I add heat, the temperature will remain constant because all of that heat is going into melting the solid. Then once the solid is a complete liquid, whenever I add heat to it, the temperature will once again increase following this specific heat formula. Then once the temperature reaches its boiling point, when I add heat, extra heat is going to go into boiling the liquid. Then once all of the liquid is boiled away and it's a gas, it'll once again return to a specific heat-like formula. So let's go ahead and look at a couple of examples. The first example says the specific heat of water is 4,186 joules per kilogram degrees Celsius, and the latent heat of vaporization for water is 22.6 times 10 to the 5th joules per kilogram. The question asks us to determine the amount of heat that's required to boil 2 kilograms of water if the water starts at 100 degrees Celsius and if the water starts at 0 degrees Celsius. So if the water starts at 100 degrees Celsius, the problem is pretty simple, because 100 degrees Celsius, remember, is the boiling temperature for water. So whenever we add heat to the water, because it's already at the boiling temperature, all of this heat is going to go into boiling the water away. So the only heat that we need to add is the latent heat, which is given by the mass times the specific latent heat of vaporization. So this is just going to be 2 kilograms times 22.6 times 10 to the 5th joules per kilogram. And if we plug this into a calculator, we see that the heat is 4.52 times 10 to the 6 joules. So this is the amount of heat that you would have to add to boil water that is already at 100 degrees Celsius. Now if the water starts out at 0 degrees Celsius, we have to first add heat to bring the water up to its boiling point. So the total heat that we have to add is going to be equal to the heat that's required to bring the temperature up to 100 degrees Celsius. So this is the mass of the water times the specific heat of the water times the change in temperature of the water. And this is going to be 100 degrees Celsius plus the mass of the water times the specific latent heat of vaporization. And if we go ahead and plug all this into a calculator, remember this is 100 degrees Celsius, we'll see that this is going to be equal to 5.36 times 10 to the 6 joules. And so basically, what this example shows us is that when you boil water away, there's a whole lot more heat that's required to boil the water than is required to change the temperature. So for example here, we've taken the water from its freezing temperature all the way up to its boiling temperature and then boiled it away, and we needed basically 5.4 times 10 to the 6 joules. And if the water already started out at its boiling temperature, then the heat that was required was 4.5 times 10 to the 6 joules. So basically, you only need about 1 times 10 to the 6 joules to bring the water from freezing up to boiling, and then you need another 4.5 to boil it away. So you need a lot more heat to boil the water than to bring it from its freezing point all the way up to its boiling point. So let's go ahead and look at one more example of latent heat. This example says, a thermos contains 0.15 kilograms of coffee at a temperature of 85 degrees Celsius. The specific heat of the coffee is 4,186 joules per kilogram degrees Celsius. To cool off the coffee, you drop 22 grams of ice that is initially at 0 degrees Celsius into the thermos. Assuming no heat leaves the thermos, determine the final temperature of the coffee after the coffee and the ice achieve equilibrium. So let me go ahead and open up a blank screen for this. So in this example, we're given that the mass of the coffee is equal to 0.15 kilograms, and the mass of the ice, this was 22 grams, so that's 0.022 kilograms. We're told the specific heat of the coffee and the water are the same, and they're 4,186 joules per kilogram degrees Celsius. And the latent heat of fusion for ice is 33.5 times 10 to the 4 joules per kilogram. And the initial temperature of the coffee is equal to 85 degrees Celsius, and the initial temperature of the ice is equal to 0 degrees Celsius. And what we're asked to do is solve for the final temperature of the ice and coffee. So again, this is just like the previous thermodynamic equilibrium problem. The idea is that energy will be conserved, so we can say the change in the total energy is going to be equal to 0, and the change in the total energy is equal to the change in the heat of the ice plus the change in the heat of the coffee. So since this has to equal 0 joules, we see that the change in the heat of the ice is equal to minus the change in the heat of the coffee. So basically what this equation is saying is it's saying the heat that's given to the ice is equal to minus the heat that is lost by the ice. So that's where this minus sign comes from, because the heat that's gained by the ice is lost by the coffee. So the only difference between this one and the previous thermodynamic equilibrium problem is that the change in the heat of the ice will include a latent heat. So the change in the heat of the ice, first the ice has to melt, so the heat that's required to do that is the mass of the ice times the latent heat of the latent heat of fusion, plus the mass of the ice times the specific heat times the change in the temperature of the ice. And I'm just going to leave the specific heat as a C because the specific heat is the same for the ice and the coffee. And the change in the heat of the coffee, so we have minus that, it's going to be minus the specific heat of the coffee times the mass of the coffee times the change in the temperature of the coffee. So this is the mass of the ice times the latent heat of fusion plus the mass of the ice times the specific heat times the final temperature of the system minus the initial temperature of the ice. And the initial temperature of the ice is 0 degrees Celsius, so this will be 0. And on the right side we have minus the specific heat of the coffee times the mass of the coffee times the final temperature minus the initial temperature of the coffee. So just like before, I want to take everything that has a final temperature and move it to one side of the equation. So first, let me just go ahead and multiply all of this out. So if I do that, I have the mass of the ice times the latent heat of fusion plus the mass of the ice times the specific heat times the final temperature. And I don't have to worry about this because I'm going to multiply by 0 degrees Celsius, so that'll just be 0. On the right-hand side, we have minus the specific heat of the coffee times the mass of the coffee. Actually, again, those specific heats are the same, so I don't need a subscript here. Times the final temperature of the system. And then here we have minus a negative, so it's going to be plus the specific heat times the mass of the coffee times the initial temperature of the coffee. So I want to take everything that has a final temperature and bring it to one side. So this has a final temperature and this has a final temperature. So I want to add this over to this side and I'm going to subtract this number over to the right side. So when I do that, I'm going to have the mass of the ice times the specific heat of the ice times the final temperature. So this term is going to stay on the left side. I'm going to add this over to the left side. So I'm going to have plus, so I'm going to add it, times the specific heat times the mass of the coffee times the final temperature of the coffee. And this has to equal, so I'm subtracting this over to this side. So I'm going to have minus the mass of the ice times the latent heat of fusion plus the specific heat times the mass of the coffee times the initial temperature of the coffee. So finally, I'm going to factor out the final temperature on the left side. So I have the final temperature times the mass of the ice times the specific heat plus the mass of the coffee times its specific heat is equal to minus the mass of the ice times the latent heat of fusion plus the specific heat times the mass of the coffee times the initial temperature of the coffee. And to solve for the final temperature, I'll just divide all of this off. So if I do that, I see the final temperature is equal to minus the mass of the ice times the latent heat of fusion plus the specific heat of the coffee times the mass of the coffee times the initial temperature of the coffee divided by the mass of the ice times the specific heat plus the mass of the coffee times the specific heat. And if I plug all these numbers into a calculator, I'll see that the final temperature is going to be equal to 63.9 degrees Celsius. So at this point, I think I'd like to end this video, and in the next video, I'm going to discuss different ways that heat can be transferred from one object to the next.